A little break.
I'm nervous about that.
We're rolling.
No intro music or anything?
Didn't bring the band.
Good afternoon, everybody. How's everybody doing today? Good. My name's Jim Kane. I'm with Dan Reiser today, and today we've been asked by Kyle and Chris to come and talk a little bit about steelmaking. Dan and I both work for Elwood Quality Steels. We're located in Newcastle, Pennsylvania, which is a little bit north of Pittsburgh, in western Pennsylvania. And we have a melt shop, and we make bottom poured carbon, alloy, and stainless steel ingots. The majority of our ingots are used in the open die forging and ring rolling industries. And Scott Forge is one of, if not our largest, customers of these ingots. So the opportunity to come and talk to you guys and explain a little bit about steelmaking in general, and then with a focus of Elwood Quality Steel's process to kind of give you guys an idea of what we're doing and how what we're doing affects Scott Forge and Scott Forge's products and Scott Forge's success as a company. So, without further ado, great steel equals great forging. As a melt shop, what we do is a foundation for how Scott Forge can be successful. If the steel supplier, ourselves, EQS, can do an excellent job, state-of-the-art processing, controls, to provide the highest quality material to Scott Forge, that's going to allow you guys to take your excellence and produce state-of-the-art in forgings and be successful to your customers. If, as a steelmaker, we have trouble and we provide sub-quality material, nothing that you guys do in the forging aspect or machining will be able to undo what was already done in the melt shop. Luckily, that's not the case at Elwood Quality Steels, and the products that we are supplying you guys are working well. But just kind of go through the process and talk a little bit about some of the steps and variables that will have an impact on the incoming steel quality that you guys will receive. How is steel made? First off, who knows what steel is? You guys Kyle's been teaching you metallurgy. Have you guys talked about steel and what steel is? Easy. Not all at once. So steel is iron, right? What combines with iron to make steel? Carbon. What else would you put in there? One other key element for sure you want to have in there.
Sulfur.
Manganese.
Oh, manganese.
Manganese, that's right. You can also add other alloys as well. Chrome, nickel, moly for strengthening and for different mechanical properties, vanadium, other microalloys. And ultimately, making a grade of steel. Later, Dan's going to walk you through how we would calculate and how we would actually make a heat of steel, a specific grade of steel. But before we get to that, the primary foundation of steel is iron. And we want to talk about how steel is made. First, you need iron units. Iron units can be processed in really break it down into two different ways. One, iron from the ground, using iron ore, where you take iron and refine it from an ore in a fully integrated steel plant, maybe something similar to, you guys might be familiar with in Burns Harbor, somewhere in Gary, around there, very large facilities. The other option is to recycle existing steel through scrap and using an electric arc furnace. So the integrated process is what's called a basic oxygen steelmaking. Again, these are these large integrated plants. Their scale is huge. It's phenomenal. To build a plant like this today would be $4 or $5 billion. That's how the magnitude is. And to be able to justify that kind of expenditure, you need to be making very large heats, 150 to really closer to 300, 350 tons per heat, and able to produce over 4 million tons per year. So it's very high volume. Flat rolled producers making steel for automotive companies, things like that. And we're going to talk about that process in a moment. The other process is using an electric arc furnace. And these again are primary melting, where you want to take your starting material and make it into liquid iron and eventually into liquid steel. The electric arc furnace, typically smaller. This became popular in the late 50s and early 60s when technology to make large transformers became readily available, and the scale of the electric arc furnace could increase from very small 5 or 10 ton heats to be able to get to a little bit more scalable volume, typically 25 to 150 ton for electric arc furnaces. They have them larger, 200, 250 tons, but primarily really going to be in that 50 to 150 ton range. And what the electric arc furnace does is it takes recycled scrap. At EQS, we melt using an electric arc furnace, and that's really what we're going to focus on today after going over the basic oxygen steelmaking. So we'll buy scrap. We buy scrap from Scott Forge. We recycle our own scrap. We buy scrap from scrap dealers, automobiles, ships that are being dismantled, any type of steel that can be cut up and reused. We are reusing it and making steel for ingots that end up in Scott Forge. With the smaller heat, the annual production scale can be smaller. Usually 200,000 is probably on the lower side, in the range of 200,000 to maybe 1 million tons per year. At EQS, 2008, everybody always refers to 2008, haven't really accepted 2009 yet. We produced about 435,000 tons of steel at EQS. We also have a sister plant, Elwood National Steel, that produced about another 90,000. So pretty much 500,000 tons per year coming from Elwood Group melting. The advantage, one advantage, is to touch base before we leave this. With the smaller heat size, and an advantage for Scott Forge, I don't want to make this into a sales pitch, but you guys have used many different grades. How many steel grades would you guys use, Chris?
Technically, we have about 950.
950, okay? So there's a lot of different grades going in a lot of different directions into a lot of different products. So, if we were in this basic oxygen steelmaking, making 300-ton heats, 300-ton heats times 900 grades, obviously that's oversimplistic, that's a lot. But by having a smaller heat size and being able to use an electric furnace as efficiently on a smaller scale allows some flexibility. So we can make smaller lots of many different grades at many different times, which helps as far as helps with inventory control and just overall business management by keeping things on a smaller scale and allowing things to be flexible. And just kind of give you an idea, this coming back to 1950s, say, there used to be a process really not used anymore, I don't think anywhere in the world, an open hearth process. Then there's the basic oxygen steelmaking process, and then the electric arc furnace process. And this is percent of steel, sorry, I use my pointer. This is percent steel production, and then the different types. And you can see here's open hearth. It was at one time it was almost pretty much the accepted way of making steel. Now it's virtually zero. It's gone away. It's an extinct dinosaur. The basic oxygen steelmaking again gave rise as open hearth went, and now it's began to dwindle a bit, although still 40% in the U.S. Electric arc furnace, again, as technology to make larger and larger transformers became available, as mini mills, large mini mills began to come on board, companies like Nucor, Steel Dynamics, that are also making flat rolled and structural steel for reinforcing rods, I-beams, making flat rolled again for automobiles, for appliances, is now about 60% of North American production. We talk about the combination of blast furnace and basic oxygen steelmaking. This starts basically from the ground, literally from the ground up, where you'll take iron ore, coal, which is then converted to coke, and then limestone. And you take those three basic elements and combine them. First off-site, we don't have it pictured here, but effectively go through the short version of this. They combine those three elements. And what happens is they put it in a sinter plant, and then they heat these, and they begin to work together effectively. So you have iron ore, which is iron and oxygen, and then you have coal, which is primarily carbon, and then you have limestone, which is primarily calcium. And these begin to work together, and they start to heat them and kind of start a reaction going. And then they take this, and then they take this in a little skip car up to the top of this vessel, which is a blast furnace. Has anybody seen a blast furnace before? Driving, maybe in by Gary, Indiana, down in east. These are very large. I should have had a nice picture. These are generally very large, large tubes, maybe 8 stories, 10 stories tall, usually in banks of 4, 5, 6 together. And when these operate for a very long time. We talked about the commitment financially to build an integrated steel plant, $4 billion, over 4 million tons. A blast furnace, to operate efficiently, once this reaction that we're going to talk about starts, it can go on for 5, 6, 8, 10 years, continuous operation. And what's happening is what we want to do in the blast furnace is we want to take this iron ore, this rock effectively, which is iron and oxygen, and we want to get rid of the oxygen. We want to reduce this ore to pure iron. So we can then take it to the next step, which is the basic oxygen furnace, where we'll then begin the steelmaking process. So what we're doing is we're taking the iron ore, combining it with the carbon in the coke, and they're already heated, and then we dump them in here. At the bottom, there's very hot air getting blown in here. And this hot air blows up through here, and as this falls, this begins to heat. And as that gets hotter and hotter, the carbon reacts with the oxygen in the iron ore to tie up and make carbon monoxide gas, leaving just the iron. So it's a chemical reaction that takes the oxygen, the carbon and the oxygen react, and then it leaves pure iron. It's a continuous operation. So we're continually dumping this into this large vessel, this blast furnace vessel, and then once we start accumulating down here this hot liquid iron right here, eventually it gets to a certain point, they tap it, and if you can look right here, just to give you an idea of the scale, you see this picture right here? That's a railroad car right there. And it's a special design, usually it's a torpedo car, and they pour the liquid iron into this torpedo car, and then it travels over to another building or the next building, which is where the basic oxygen furnace is part of the basic oxygen steelmaking practice. So here is our vessel for basic oxygen steelmaking. What happens is if you see this shadow right here, this furnace will tilt, and then in addition to the liquid iron that we had, we'll also use scrap in this process as well. So we put scrap down here on the bottom, and then the hot liquid is poured into here, and this oxygen lance comes down. Because what we need to do in the previous step, we were able to get rid of the oxygen by having the carbon react with it, so we're left with the iron. But a byproduct of that is we have iron, but we also have very high carbon. So now we have to get rid of the carbon to be able to get to iron to be able to begin to make the steel. 5–6% carbon probably, 3, 4, 5, somewhere in that range. Much higher carbon than we would want for any grade of steel that we would make. So how are we going to get rid of the carbon that's in the liquid iron?
Add oxygen.
Add oxygen, that's right. So what we're going to do is we put some scrap in here. Again, if you're in a steel plant, flat roll plant, you have lots of scrap laying around. So one of the things you want to be able to do is recycle that, not for free, but take that scrap, charge it back into your vessel, and then again pour the liquid metal into here. Here's this vessel, and then coming down here is a lance. This lance blows oxygen, reduces the carbon that's in the iron, and then once that blow is done, the furnace tilts again, and it's tilted sideways. If you see right here, this is a tap hole, so this is going to tap all the way down here, and then the liquid steel is going to come down into what's called a ladle, which I have a picture of right there, is poured into a ladle, which is a holding vessel for the liquid metal, which in this case is iron, and then moves on to secondary refining. And then you begin to make the grade of steel that you're going to make. Pretty brief synopsis there on blast furnace and basic oxygen steelmaking. The other process, and this is where we're really going to focus on today, is the electric arc furnace. Electric arc furnace, no, you can use blast furnace products, but primarily you're using, and it would be cold, beach iron or pig iron or something that is poured from the blast furnace and then allowed to cool and then is used again. But primarily it's 100% scrap. We're recycling everything. How the electric arc furnace works is there's 3 electrodes that are lowered into the scrap, and you strike an arc, an electric arc between the electrodes and the scrap. And as that electric arc goes through the scrap, there's resistance to that electricity. The resistance builds heat. You build enough heat that you begin to melt the scrap. And again, as we talked about, the economy size is small, furnace size typically 40 to 150 tons. This is an overview of the process at EQS. We have what we were just talking about. We have the primary melting, which is in the electric arc furnace here. Here we start with charging of the scrap. So there's a scrap bucket that loads the scrap into the furnace. We melt this, going from scrap to liquid as fast as we can, tapping the liquid steel into a ladle. Then we go to a ladle furnace where we add our alloys. And again, I'm just kind of giving you a quick overview. We add our alloys, and we begin heating and also deoxidizing, again, which we'll talk about more. The next step is the vacuum degassing, where we're removing hydrogen. Then we move to a second ladle furnace station, where we do all our final adjustments, make sure everything is absolutely perfect. And then we take the ladle and we bottom pour our ingots. In this case, it's a ladle. You can see the steel goes through what's called a trumpet and then into runners. And then the steel enters into the mold from the bottom. Again, we'll talk about this. And we fill the ingots up. We allow the ingots to solidify. We thermally cycle the ingots and then ship them to Scott Forge. You can see this a little bit more in depth. With our video. Good. Turn it all the way up. So we got about an 8-minute video. You can basically explain and give you a tour of EQS. So since we can't go see the shop, I thought we'd bring it to you.
Located in Newcastle, Pennsylvania, our steelmaking process begins with the receiving of steel scrap. EQS accepts this material only after it is scanned for radioactivity using specially designed Geiger counters. In addition, there are also radiation checks directly prior to the scrap entering the mill.
Double-click the picture.
Before scrap material is charged, and in a chemistry sample taken at the end of the primary melting process. Scrap material is also tested for chemistry compliance using a handheld X-ray fluorescence testing device. If accepted, the scrap is unloaded and separated into bins according to the alloy content, density, and size. These bins are conveniently located inside the mill, which protects them from the adverse weather conditions. Our melters use a computer model to optimize the scrap charge for each of the various grades and heat sizes made at EQS. Once a charge is designed to our customer specifications, scrap is loaded into the electric arc furnace. This ultra-high powered furnace employs a twin hydraulic lance injection system to blow oxygen and carbon into the furnace. This injection system, combined with 3 separate oxy-fuel burners, achieves fast, efficient melting. Phosphorus, an impurity, is removed from the steel bath by refining it into the foamy slag as oxide, which is continuously flushed from the furnace. In less than an hour, the molten steel is ready for tapping into the refining ladle via the eccentric bottom tap hole, or EBT. The entire furnace is tilted as the steel is tapped into the ladle, along with a specific amount of alloys and oxidizing agents calculated from our computer model. A reducing top slag is also automatically added when tapping is complete. The ladle is then transferred to the ladle refining station. Here at the ladle refining station, the alloy calculation program consistently brings the chemistry to the aims supplied by our customers. The alloy additions are automatically weighed and transferred from bins into a hopper and then charged into the ladle. To ensure chemical and temperature uniformity, the process requires induction stirring. Induction stirring mixes the steel beneath the slag cover using magnetic forces. In addition to helping to create a uniform bath, the induction stirring also aids in the removal of non-metallic inclusions by creating opportunities for them to be absorbed into the reducing slag. Next, the ladle is transferred for vacuum degassing. The liquid steel is covered by the degasser hood, which is sealed onto the ladle. The pressure is lowered to near vacuum conditions, which facilitates hydrogen escaping from the steel. For effective hydrogen removal, a very high stirring energy is achieved by a combination of argon bubbling and induction stirring. This action is maintained for the entire degassing cycle. Hydrogen samples are taken and analyzed after degassing to help ensure that the hydrogen levels are within EQS standards. A final test for certification is also taken from the ingot molds at the end of teaming. Once degassing is complete, the steel is transferred to ladle furnace number 2, where it may be treated via calcium or sulfur wire injection. These alloy additions can improve either the mechanical properties or the machinability of our steel, depending on our customer's application. At ladle furnace number 2, the steel may be reheated, and final alloy adjustments can be made before the liquid steel is teamed from the refining ladle into the ingot molds. The teaming temperature is controlled to within 5 degrees Celsius. A precisely controlled teaming temperature is critical for producing high-quality forging ingots. In the teaming bay, dry, clean molds are set up for each specific heat. The ladle is centered over the trumpet, and the slide gate is open. As part of our continuing effort to produce high-quality clean steel, argon shrouding is used to help protect the liquid steel stream from reoxidation and hydrogen pickup during the teaming process. All ingots produced are bottom poured at a controlled rate, and steel pourers utilize handheld data entry devices to continually monitor the teaming operation so that maximum consistency can be achieved. EQS maintains a large variety of mold shapes and sizes in order to accommodate the various ingot requirements of our customers. After solidification, the molds are stripped, and the ingots are tagged with identifying information, including a barcode for tracking purposes. In between uses, most ingot molds are cleaned using a flailer which removes buildup and debris inside the mold. This process, along with periodic grinding of the inner mold walls, enhances the surface quality of future ingots. Car bottom furnaces are available for slow cooling, and specifically designed annealing cycles for each grade enable us to supply stress-relieved ingots with uniform hardness. After every ingot is thoroughly inspected, they are either shipped hot or slow cooled. Hot shipments have been made as far as 200 miles away and help our customers save on reheating costs. For slow-cooled ingots, EQS has the capability to surface condition, flame cut, or salt cut ingots to meet customer requirements. In addition, the chemical composition of all cold ship material is checked with a spectrotester prior to leaving the mill. EQS delivers ingots by truck, rail, or sea, both domestically and outside the U.S. The EQS quality control system has been certified to ISO 9001, an internationally recognized quality standard. This system was implemented using a highly trained workforce and utilizes state-of-the-art equipment, including an in-plant chemistry lab, a geometry testing lab, and a scanning electron microscope complete with EDS elemental analysis capability. As an industry leader, EQS takes pride in knowing that our steel is utilized in several critical applications. That is why we are continuously striving to improve both our process and our product. With a focused effort on providing high-quality material and maintaining a competitive advantage, EQS and its employees are committed to exceeding our customers' expectations by making excellence an everyday occurrence.
Okay. Anybody have any questions on the video? No? Okay. Well, I'm going to ask Dan to come up here, and he's going to go back over our process, and we'll walk you through each step a little bit more in depth. And again, as we're going through this, if you guys have any questions or something doesn't make sense or seem right, just feel free to ask. So without further ado, here's Dan.
As Jim said, I'm Dan Reiser. I'm a metallurgist at EQS, and now that you've seen the video, you've seen the overview of our process, I'm just going to go through a few of the more specific areas in a little bit more detail. And as Jim said, feel free to interrupt me if you have any questions as we go through. First thing I'm going to start out with is the electric arc furnace, because that's where steelmaking starts for us. We use 100% scrap material, recycle it, and we melt the scrap material using electrical resistance to the scrap, which creates an electronic arc, which is the namesake of the electric arc furnace. And as I've shown here, the temperature at the tip of the arc is about 1800 degrees Fahrenheit. 1800 degrees Fahrenheit is extremely hot. It'll melt just about anything, including the lining of the furnace if we weren't very careful to protect the electric arc and make sure all that energy goes into the scrap rather than out into the furnace lining and stuff like that. Just to reiterate some of the advantages of the electric arc furnace, the economy of scale is small, so we can make flexible heat sizes And again, furnace sizes typically 40 to 150 tons. So when the steel making process begins, the scrap material is collected into charge buckets and placed into the furnace. The melting of a heat, which starts from pure scrap, normally takes about 50 minutes. And as I've also noted on the slide here, the electric arc furnace is an electricity hog. It uses as much electricity per heat, which again is about 50 minutes, as an average size home would, one that has electric heating and air conditioning for an entire year. So needless to say, the cost of electricity is very important to us in the kind of efficiency and pricing we can have with our steel.
That doesn't seem like it's really outrageous. It must be fairly efficient as far as being able to only use that amount of electricity per heat.
I mean, it is. I mean, it's efficient, but I mean, it is using a large volume of electricity.
Yeah, I mean, there's different levels of arc furnaces. Ours, the one we have at EQS is one of the higher levels, which enables us to get in 50 minutes. If you had a lower level arc furnace, it would take you a little longer. Plus, we also kind of streamline things in that we use our arc furnace purely to melt scrap. We don't try to do any alloying or anything in there. We do that later on down the line, so that also helps with the efficiency.
One thing just to add, and Dan's going to talk about this too. In addition to the electricity, we also use some chemical heating. You know, those same kind of principles we talked about in the basic oxygen steel, where we're blowing oxygen to get rid of the carbon. We'll actually charge carbon units into the scrap, and then we also blow oxygen. When we first started the shop, it was 90 minutes tap to tap time. And since this time, we've continued. When we implemented that oxygen lance system, that basically took us from, it was actually, first year was 86 minutes. It took us from there just to about an hour. So almost got 15 to 20 minutes out of our tap to tap time, which is 25%. So not only are we using electricity, but we're also using oxygen and chemical heating as well for that efficiency as well. And that's just one heat. So that's 40, that's a 45 or 50 minute flash, not even a full day's production. So.
When you say oxygen, are you speaking of you're just pumping it from the outside air, or is it?
No, it's actually on site. We have an oxygen plant that makes pure oxygen. Actually, we share that oxygen plant with North American Forge Masters, because their reheat furnaces are oxy-fuel furnaces. So just on the other side of NAF, there is the oxygen plant. They have a pipe going over to NAF, and then we end up trucking most of it to ours, but it actually ended up working out the win-win scenario.
Yeah, and I mean, we use the kind of three things: the electricity, the chemical heat, and then we also have a couple oxy-fuel burners, which are more just to address cold spots in the furnace. I say cold in quotes because, again, we've got an 18,000 degree arc in there, but colder spots to keep everything more uniform. So between those three, it's a very efficient. In addition to melting scrap, we also do carbon and phosphorus refining in our arc furnace. Basically, we want to try and get the carbon level pretty low because we'll tend to pick up carbon throughout the steel making process from the electrodes, which are graphite, and from other alloys that we add. So we want to try and get it very low to start with, and then if the grade requires more, we'll add more in. And the carbon is refined, again, through blowing oxygen in it, kind of the same way as in the blast furnace. You make carbon monoxide gas as you blow the oxygen in there, and since it's a gas, it bubbles out of the bath and up into our fume hood and lowers the carbon content. We also use the oxygen to refine phosphorus, but we turn, instead of making a gas out of it, we make a non-metallic, kind of an oxide out of phosphorus, which floats up into the slag. And then we drain it off. If you remember in the video, they showed a picture of the slag door, and they had this stuff coming out of the arc furnace. That was slag coming out, and if the arc furnace did its job right, it was slag filled with phosphorus. And unlike carbon, which can actually make a steel better depending on what kind of properties you want. Phosphorus will always make your steel worse. So we just want to get as much phosphorus as we can out. If we had a certain grade that required an especially low amount of phosphorus, we might need to use special scrap that is certified to have lower phosphorus. But in general, we can just use the oxygen blowing to get the phosphorus down to the kind of levels that we're looking for.
What do you guys do with the slag then?
We collect it in a slag pot, and I think that we send that out as kind
we
of
have
waste product.
under where it's getting drained, underneath our arc furnace, there's a tap hole where the ladle taps, and then back behind here there's a slag pot. We collect the slag. Once the slag pot's full, we pull it out, we'll let it cool down. We actually have a special truck. We just set that slag pot on, and it delivers it to a recycling area. So it's we'll go back through and they recover the slag. I think there's some chrome units that there's a facility down the road that's working to recover chrome units, and then they take the remaining slag, break it up. We'll use it for non-critical. Can't use it in a road bed, but we use it for like slag for the side of roads and different things like that. So it gets used.
Yeah.
One other point about the phosphorus, we talked about low phos. Depending on how far we have to get the phos down, we may need to spend longer time in the arc furnace. So if it's a standard grade, we might be in the arc furnace for 50 minutes, but if we need to work to 008 or a very special grade, power generation rotor steel or something, we may need to take even longer time in there to get the phosphorus down.
So once we have the liquid steel to a level where the carbon and phosphorus levels are where we'd like them, we're ready to pour the steel out into a ladle. Traditionally, this was done via a spout on the arc furnace, and you would tip the arc furnace kind of like a tea kettle and pour out the steel into a ladle. But a lot of the newer arc furnaces, including the one we have at EQS, have an eccentric bottom tapping feature, or EBT, which is where we have our spout kind of at the bottom of the furnace, but it's off-center, or eccentric, and we take the steel out from the bottom. And the reason it's off-center is to try to cut back on any kind of whirlpool effect that we would have in the arc furnace, because that can wear down the lining of the arc furnace, which we generally want to protect that as much as we can. One of the big advantages of eccentric bottom tap furnace is that you get to keep most of the arc furnace slag, which is the stuff that floats on top and has the phosphorus. We tap some of it out into a slag pot, but there's still some on top. But we get to keep most of that in the arc furnace. It doesn't go into the ladle. And the reason we want to keep that out is because that's where most of our phosphorus has gone. And if it stays, it goes into the ladle and stays there, it can revert back into our liquid steel. So if we didn't have the bottom tap, what we have to do a deslagging operation, which is you take a rake and you rake off the slag and put a new one on top. This eliminates that kind of operation and saves us about 20 to 30 minutes per heat. There are some, we do have the capabilities still to deslag heats, because we have to do it every once in a while if we need to drain the furnace completely for any reason. That, of course, includes the arc furnace slag, so we'll have to deslag that heat. But I'd say over 90% of the heats that go through, we get to skip that deslagging operation.
So you're not draining it 100%.
Well, that gets back to that's the third point. I didn't want to jump too far ahead when we were answering your question. But we have to leave 5 to 10 tons of liquid steel in the furnace to avoid vortexing over that oxidized slag. So for the next heat, we have this scrap coming in, but we already have essentially 5 to 10 tons of that next heat already melted. So we charge our scrap on it, which, because of the heating, think about having ice cubes. I have an empty glass and I have a glass that has maybe an inch of boiling water in there. If I dump ice cubes into it, the ice cubes that go into that boiling water are going to melt faster than the ice cubes that are just going into that empty glass. So we do get also gain productivity and efficiency in the primary melting, as well as from the secondary refining. That's where the real advantage was. This was such a valuable investment. Our shop was started in 1985. We made our first heat in December of 1985. And this technology was just becoming available. 6 years after we started, we scrapped that brand new arc furnace and replaced it with this furnace at a significant cost. But the return on investment was so great that it was very obvious that it was the right move to do. Sorry, man.
Yeah, we do utilize that liquid heel to kind of kickstart the next heat that goes in there. And you'll see that in this slide here. This is an animation that's going to show you kind of the tapping mechanism of the EBT furnace. You'll also notice that we take this opportunity to add in, to do some of our alloying, since when you're pouring the heat into the ladle, you got some inherent good mixing energy going in there because steel's coming in a stream and filling up the ladle. We want to take advantage of that to try and mix in some alloys, not all the way up to the ranges we want, but kind of to give us a good start. So we'll throw some alloys in there. Also, before we even put any steel in the ladle, we'll typically put some aluminum in there, or sometimes we use silicon for a deox agent. What that does is it ties up any of the free oxygen that's in the liquid bath to keep it from, if you have free oxygen in liquid steel, it tends to make it bubble and crack and stuff like that. And actually, if you put in aluminum, it's what's known as killing the steel. And the reason it's called a killed heat is because you took that oxygen out, it's no longer active and bubbling, which can be a safety risk. So we want to make sure we deox that by throwing in some aluminum right away. So here we go. The furnace is tapping, put our aluminum in there, or tilting I mean. Now it starts to tap. Put in some alloys. Also throw in some lime to put in to generate a slag cover on there. And then if you saw, we tilted the furnace back before the slag level, which is this brown part, got down to the level of where the spout was. I'll just rewind and show that again so you can see that. But we'll want to tilt the furnace back to keep that arc furnace slag in the furnace. We tilt it back, close it off, and then we're left with the liquid heel still in the furnace. And we throw some lime in there just to cover the steel, because we do want some sort of slag on top. So that's why we do throw some lime in at the same time. So after tapping, the ladle's moved over to a ladle refining station, which is where we do most of our alloying and get the steel up to any kind of grade that we're trying to make. The ladle station is refined with, or is equipped with electrodes just like the arc furnace, as you can see here. But these aren't really for melting anything because we already have a liquid steel bath. These are just to kind of maintain the temperature. In addition, to kind of help keep the temperature uniform and also to help keep the chemistry uniform when we do add in some alloys, we'll utilize a process called induction stirring. And induction stirring, remember from the video, we take magnetic forces to kind of turn the steel over and roll it around in the ladle. It's basically mixing the steel without putting in something mechanical to stir it around, using magnetic forces to stir it. And have an animation of this as well. One of the benefits of this process is there's going to be some non-metallics in the steel from when we melted down the scrap, and not all of them will be able to float up into the slag just because not all of them have enough buoyancy to get up there. But when we're mixing the steel with induction stirring, we allow opportunities for those non-metallics to get up into the slag and kind of clean our steel that way. And you can see that here. They're exaggerated in size, of course, but as we mix them around, kind of get them to interact with that slag layer and clean out our steel a little bit. All right, so now that we're at the ladle refining station, we start to add in our alloys to make our grade. We have over 300 grades of steels that we actively make at EQS right now. That number always changes. As Chris said, you guys have 950 different grades you make here, but we have to be very flexible in all the different kind of steels that we make. And that's one of the things that makes EQS unique, is that we can make everything from your plain carbon steel up to your stainless steels. I'm just going to go through a little bit of the basics of how we do alloy calculation, because it's pretty fun, and I'm sure you guys would be interested. First off, there's two main types of alloy calculation: computer-assisted and manual calculation, and we use both at EQS. We don't do the manual calculations because we don't trust the computer or anything like that, but it's always nice to have a backup, and we want our operators to know if they see a value that isn't correct, to kind of be able to recognize that and say, that doesn't look quite right. So we always let the computer calculate how much of each alloy we need, but we do it by hand as well. And I'm going to go through a real simple example here of how we would do that. This is a pretty simple grade here. It's just a 1045 steel. These are the ranges that we're trying to hit. There are a lot of other elements with this particular grade that we need to worry about and make sure we don't get too high a level on. Things like phosphorus and things like that we want to keep low. But these are the only things in this grade that we have a range that we try to hit. You know, we have a minimum and a maximum. So I'm actually going to use the arc furnace melt-ins from an actual heat that we melted recently, heat W3814, melted at EQS and sent to Scott Forge. So what happens is when the ladle arrives at the ladle refining station, we do a chemistry test right away to see what we're starting with. And on this particular heat, we had our carbon at 0.37, manganese 0.617, silicon 0.238, and aluminum 0.0215. Looking at the ranges, silicon and aluminum are within the ranges we're going for. So we don't need to add anything there. We'll keep tabs on them to make sure they don't vary out of those ranges, but they're good. Carbon and manganese we're going to need to add into to get into the ranges we're looking for. So we'll go through the carbon first. Carbon is added as a pure form, pure carbon, which we use graphite. You could also use diamonds, because diamonds are pure carbon, but those are a little bit more expensive, so we use graphite. And for simplicity's sake, we're saying we're starting with a 50-ton heat, or 100,000 pounds. So multiplying by how much carbon we have 370 pounds of carbon in the heat. If we take the AIM carbon, which is what was in the middle of that range, which is 0.46%, we figure out we need 460 pounds of carbon, or we need 90 more. We need to put 90 more in order to get into our range. But we're not going to add in the carbon at this point because we always add that in last. We'll typically get some carbon from some of the other alloys we add, and we also get some carbon from the electrodes as we go through. So we want to figure out all the carbon that's coming from other sources and add it kind of late in to make sure that we don't go over the range we're looking for.
So your electrodes are
Graphite. Mm-hmm. Yeah, they're graphite and they're consumable. We go through on the arc furnace, or when you say like 8 or so a day.
Yeah, the electrodes kind of screw together and they're consumable, so they're always just, you screw in and they keep going into the bath. Probably section-wise, a section is probably about 36 inches, I'm guessing.
Yeah.
No, it's about 36, 40 inches. I have to say, but yeah, about that. So
yeah, so we will get some.
It's a special, it's a directionally solidified graphite. It's really, if you've ever had a chance, it's a very intricate process to make these, and the idea is that the way they produce them is to optimize flow of the electricity through and maximize conductivity through.
What's the liner of the furnace?
The lining of the furnace is it's a ceramic. It's mostly magnesium oxide base, but there's a couple other components. But it's all stuff that is ceramic material, so it's meant to take the abuse of the heat. We obviously have to replace it every once in a while. We re-change out the lining of the furnace 2 or 3 times a year, depending on how much we're using it. But we try to get by as often as possible with just doing little repair work. We actually have a gunning material that we put in and we spray around the furnace lining to kind of beef it back up and keep it stronger, so we can go longer without replacing it, because that's a big process. We got to shut everything down, rip out the lining, put in a new set of bricks.
Typically at full production, we'll have to take 3 outages during production, and then a 4th, it will do a full reline on a summer shutdown. The other thing, just to kind of point out, to give you the whole picture, the arc furnace itself is a steel shell, which inside that steel shell we have these panels, and the entire furnace, entire roof, as well as these hoods that you see coming down, they're all water cooled as well. Yeah. Because we have the refractory. Obviously the refractory holds the steel and protects the hot liquid steel from burning through. But just the heat that's generated, if that furnace was not water cooled, where we have, have a whole series of a water treatment plant, a whole series of heat exchangers, we'd actually start melting the furnace. We'd erode the refractory faster. We'd end up melting the furnace almost as fast as we melt the scrap. We have a whole series of different safety things with thermocouples. If we do get a hot spot, we automatically drain the furnace. So there's a lot of preventative side of things to avoid what would be disaster, where if we were to burn through the side of the furnace, because when that happens, you don't get to pick where you burn through, and usually, the one time we did that, it would be in the worst spot where you have several you got a lot of lines and different things. So it's pretty important to maintain process monitoring of that stuff.
Yeah, as Jim said, we've got thermocouples embedded underneath the brick and stuff like that. So we're constantly monitoring, and if something's getting a little hot, we might not shut down production, but we'll just pause and do a repair or something like that. Try to avoid doing a reline unless we absolutely have to.
Well, I'm sorry. One other thing on the gunning machine. It's another thing that we've done. Used to be, you would start to wear, and usually you wear right at the slag line. That's the most erosive area. And as you get into this campaign, you're having to do more and more maintenance. And what we used to do, basically, gunning the furnace would involve effectively taking a fire hose, climbing up onto the side of that arc furnace, and then blowing that gunning material through the hose for the entire furnace. It'd take an hour and a half. I don't know about you, but I would not want to spend an hour and a half gunning a 3,000 degree furnace. It's a safety issue. It takes an hour and a half. So what we ended up doing is replacing that practice. We actually have a refractory robot that comes up, goes down, and is lowered into the furnace, and can basically automatically gun the entire furnace if needed in 20 minutes. The advantage to Scott Forge for that is, when we're late in a campaign, instead of us having to take an hour and a half at the end of a production day to gun the furnace, now it takes us 20 minutes. It takes us 50 minutes to make a heat. We just got an extra heat of production for Scott Forge by making that investment into that gunning machine.
Now, is your facility 24/7 as far as production?
We'd like it to be, yes. Yeah, it is. Right now it is, yes. 2009, we ran off-peak during the week and around the clock during the weekends because of business conditions. But since the middle of December, we've operated 24 hours a day, 7 days a week. So.
And by off-peak, Jim, means when electricity is less expensive, which is at night and over the weekends, since electricity is a big part of making steel. It's still more efficient if we can run 24/7, but if we can run partial, we want to work off-peak.
How many watts your big furnaces for the melter?
That's the 40. That's the transformer is 42 MVA.
Okay.
All right, so back to the alloy calculation example. So we figured out how much carbon we need to put in eventually. Going to the manganese, Manganese is added as ferromanganese, so it's not just pure chunks of manganese we're putting in there. It's a mixture of manganese, iron, and carbon. So we use the same process and figure out we have 617 pounds and we need 750 pounds. So that's 133 pounds we need of pure manganese. So we got to convert that now into ferromanganese. So we just divide by the amount of manganese in the ferromanganese and figure out we need 166 pounds of ferromanganese. So now we have to determine, since there's a carbon component to the ferromanganese, we got to figure out how much carbon we're adding when we add in our ferromanganese. Doing the same thing, we figure out it's 11.5 pounds of carbon powder. So we take that number and we go back and subtract it from the 90 pounds we would need to add as pure carbon. And so since these are the only two things we're adding in, we can now add in our carbon as 78.5 pounds of graphite. Now ideally, at this point, everything's within range and we can just go forward with the steelmaking process. But we're going to take another chemistry sample and just see where we're at, because sometimes you don't get the recoveries you're looking for, or the heat weight might be a little off. So we try and be as efficient as possible with the alloy calculation to make sure we don't have to go back and tweak very much. But if we do, we need to make sure we have the new steel weight calculated, which is the original steel weight plus all the adds that we figured out. And this is for a simple grade. For a more complicated grade like a stainless steel, we know we're going to have to do more than one add, because we got to creep up to our ranges rather than just trying to do them in one swash, because we might exceed the maximum. And that gets really hard to fix, because then you got to add in dilution iron or something like that to dilute down your alloy content, which is much harder than adding alloys to get up into your content. So after we have the alloys or the grade chemistry mixed up to where we like it, we send it over to vacuum degassing station. The vacuum degasser has one main function, and that is to get hydrogen out of our melt. Hydrogen is along the same lines as phosphorus, in that it's always bad for steel, and but it's very hard to get out of steel because hydrogen is the smallest element, right? So it just sits in the steel and hides, and makes it really hard for us to get out. It's kind of like if you had fine particles of dust in a carpet and you're trying to get it out with a broom or something like that. You could sweep all you want, but you just can't get to those little particles. So what you would do in that case is you use a vacuum to suck out the dust particles. And it's a little different because hydrogen's a gas rather than a solid, but that's effectively what we do. We take, we put a lid over the ladle and draw a vacuum inside, and create a driving force for the hydrogen, which is a gas, to leave the steel bath and try and fill that space in the vacuum. But in order for this to be effective, we need to expose as much steel as we can to the vacuum. So we'll use a dual process, which was mentioned in the video, the induction stirring process, which again turns the steel over and it'll expose that little window of steel to the vacuum. But we also do argon bubbling, which is we jet in argon from the bottom of the ladle, and as a gas, it bubbles up through the liquid, hopefully capturing some hydrogen as it goes up and up into the vacuum and out, and that cleans out some hydrogen that way. It also disrupts the surface of the liquid steel, which again exposes more steel to the atmosphere and or to the vacuum, and lowers the content of the hydrogen content of the steel. And this is just a video or an animation to show this process. You do stirring and expose this little window here to the vacuum, and then send bubbles up to disrupt the surface and grab some hydrogen on its way up. The hydrogen content we generally shoot for is below 2 ppm, and ppm stands for parts per million. So for every million parts in this steel, only 2 of them are allowed to be hydrogen, which is a very small amount, and requires degassing for sometimes 30 minutes, sometimes more, to get the hydrogen down to that kind of level. And once we have it at that level, we want to make sure we minimize any exposure of the liquid steel to the air, which has hydrogen, or any kind of moisture. So we'll, after this point, we'll do our best to keep a slag cover over the liquid steel to try and just keep any extra hydrogen from reintroducing itself to the liquid steel.
The amount of hydrogen we're trying to remove, if it was liquid, it would fit in this cap. Just as a kind of give you a scope, it's not very much at all, but just that much hydrogen can wreak havoc in a forging. And we'll talk about that a little bit later.
Yeah, it's hydrogen is the enemy when it comes to steel. And, very tricky to remove, but through a lot of advanced processes, we're able to get that content very low. And
I do want to think. The other thing that results in vacuum degassing is you get very good mixing of the liquid steel with the slag. So also we're able to desulfurize and get very low sulfur contents at that stage as well, whether we want to or not. Sometimes we'll have to come back and add it back.
So after all of the melting and refining is complete, the steel is sent for teaming into an ingot mold. And as Jim mentioned, at EQS we use a process called bottom pouring. And that means instead of pouring the steel from the ladle directly into the top of the mold and filling it from the top, we open the ladle over a trumpet and have the steel flow down that trumpet into a series of runners and fill the molds from the bottom. And the benefits of this technique is you get very smooth and even filling. You don't have turbulence or very much turbulence when the molds are filling. So that helps reduce the wear and tear on the teaming hardware, which is the ingot mold and also the trumpet and things. The trumpet and the runner bars are lined with ceramics that are a one-time use steel. We run the steel through them once, and then we throw that material away. So that also helps protect the teaming hardware, because the liquid steel is extremely hot, almost 3,000 degrees Celsius, or Fahrenheit, I'm sorry. So we want to try and keep that kind of hot metal from eroding away the mold and the other kind of teaming hardware. We'd rather have it do damage on the ceramic lining that we throw away each time.
Is that also to keep the slag at the top of the...
Well, the ladle is teamed, this is the ladle here. So it's teamed from the bottom, similar to the way the arc furnace is, only it's not tilted, it's just we open a hole in the bottom. So, we drain all the liquid metal and just leave the slag in the ladle. Occasionally we have times where some slag comes out at the bottom of the ladle, and in that case we'll shut everything off and keep that slag in the trumpet, because we don't want that getting into the ingot mold. So, but ideally we just get pure liquid metal and we leave the slag in the ladle, and we dump that out afterwards by tipping the ladle over before we reuse the ladle in another campaign. So this is another animation of the teaming process, and in addition to seeing these molds filling, you'll see that first it's going to drop the first part of steel in this little canister here. We call these butt canisters, and the purpose of these is that between the liquid steel and the plates that open up at the bottom of the ladle, we put some sand in there, and that's to keep the liquid steel from eroding away the plates while the ladle is going through the various steelmaking processes. So when we open up that slide gate, the first stuff that's going to come out is the sand. And we don't want that to go into our molds because that can cause defects and things like that. So we'll use one of two processes. We'll either use a butt can, which is we empty the first bit of steel into here and then move over to the trumpet, or we'll use a cardboard tent over the top of the trumpet, which will deflect away any of the sand, and then when you get the liquid steel coming through, it'll burn through that cardboard and just start teaming into the molds. So here comes the ladle, slide gate opens, you get that first bit of steel in there, and then move the ladle over and start teaming into the molds. And you notice the two molds here are they're two different sizes and shapes, and although we typically won't mix up the setup like this, we certainly have the option to, because if you think about it, the steel's only going to fill to whatever level, you know, to the same level, no matter what size the mold is. So as long as the molds are the same height, we can use a mixed setup like this. And also, you see the steel in the trumpet only gets to that level, which means if we did have any slag coming out in, it would stay in this trumpet and wouldn't get up into the ingot molds. After the teaming process, we let the liquid metal solidify, and then we'll strip away the molds like you saw in the video, and send the ingots for, normally go through some sort of thermal cycling to keep from any kind of thermal cracking or anything happening while the steel's cooling down, and then ship them out.
How do you get the steel out of the trumpet?
Well, steel, when steel solidifies, it shrinks. And so both with the molds and with the trumpet, you'll have a little bit of a gap in between there. But what they'll do is they'll just pick the trumpet up, and then they'll have this solidified pole of steel there.
So they pull the trumpet off of, I mean, obviously if it's on a U shape, you can't,
Well,
it won't just come
well,
out
there's,
of
Well,
that's a good point. Okay.
what we'll do is, you know, we take the molds off first. If it's a mold like this, we'll have to dump it out. We can't just strip it up straight. And then we take the trumpet off, and there'll be this vertical cylinder of steel there. And normally then when they rip that out, the runner bars will come out too, and then, you know, it breaks off right here when they take the ingot away. So, because this is a very small diameter compared to the rest of the steel. So we'll be left with these kind of skeletal remains of the trumpet and the runner system, which we cut up and use as scrap in another heat.
The funnel part that you're looking at, the taper, that's not filled with steel. Because the steel will only fill as high as the mold, and we always have that trumpet part is always going to be higher than the liquid steel. The other thing is, the trumpet itself is a cast iron, and it's casting, and it has a hole in the middle. The hole is much bigger than the trumpet brick. The hole might be 8 inches, 7 inches, I'm not sure. The trumpet brick has a diameter of 4 inches. So there's about a 2-inch, 1 to 2 inch gap all around that. So when we set the trumpet brick into the trumpet, we cover the funnel, and then we have dolomite, and we pack it with just loose dolomite, which used to be sand, but because of silicosis and safety issues with silica, we use dolomite, and it just packs. So really, when we lift that trumpet up, it almost just falls right out. It doesn't really stick unless there's some flashing or something like that. So that part just comes right out.
It's the same thing with the runner bars too. We also have the slots that are there are much bigger than what's needed for the ceramics, so that we use dolomite to pack them in there loosely, so we don't have any problems with it sticking in there or anything like that.
How long does it take before you can strip the molds, the solidification time?
It depends entirely on the size of the ingots. It can range anywhere from a couple hours to a couple days, depending on the size. We have a formula we use that calculates, based on the alloys in there, how much time it needs to solidify, and then we'll add a couple hours for a safety factor and give it a range. And there are they're required to strip the heat or strip the ingot within that time period, or else it's you know, we have to flag it as a possible quality issue, and we'll have to look into that.
Is it 100% solidified when you strip?
Yes.
Yeah, we make sure we, you know, we'll talk a little bit about that later, but yeah, the yeah, like we do the calculation. That's what the safety factors for there a little bit, and then you know, the calculation is a function of the chemistry itself, and the temperature, and then from there we have safety window, and then the operating window as well.
And we also take care to try and make sure the ingots aren't bumped or anything like that while they're solidifying, because we don't want anything disturbing that solidification profile, because then you can get anomalies and stuff like that. We want to, if you know, it's we want to leave them alone, and we do as best we can to not bump them with a crane or anything like that while they're solidifying.
Yeah, if there's any contact, a non-conforming disposition,
Yes. Yes.
usually resulting in that ingot not going where it was originally intended.
All right. Now, despite our best effort to produce clean steel, there are frequently some sort of inclusions present in the steel. And an inclusion is defined as anything that is internal to the steel but is different from the typical metal matrix. These inclusions come in two different kinds of forms, indigenous inclusions and exogenous inclusions. Indigenous inclusions are things that are different from the metal matrix but are made up of components or elements that make up the steel. For example, manganese sulfides are one thing that you'll frequently see in there. You have manganese in the liquid metal and sulfur, and when it solidifies, it can form this precipitate. That's an indigenous inclusion. Typically, these aren't things that you would worry about from a forging standpoint, because they're part of the steel chemistry, and any kind of testing that was done with that alloy probably had those kind of inclusions present. Exogenous inclusions are things that are introduced to the steel in a liquid form and become entrapped when it solidifies. And these are typically the ones that can cause problems. As I said before, we take all sorts of precautions to try and keep our steel as clean as possible. But when you think about it, we're dealing with a liquid that's 3,000 degrees Fahrenheit. And if you think of how a river can erode away, you know, a bed and cut through a mountainside over time, imagine if that river was 3,000 degrees. It would erode things away at a much faster rate. So there's all sorts of things we have in place to try and keep that any exogenous inclusions small and as infrequent as possible. But some common types that we've seen are refractory product from the stuff that lines the ladle and the runner bars and things like that. Teaming flux, which is a powder lubricant that we use in the molds to keep the steel from sticking as it rises up through the mold, and the nozzle sand that you know, we have in the ladle to protect our slide gate. Although it's virtually impossible to keep any kind of exogenous material out of the steel, we do have lots of controls in place to make sure anything that gets in there is hopefully small, and anything that is exogenous would typically be picked up by a UT inspection or ultrasonic testing. After forging is complete, you do a UT test. If there's anything exogenous that could cause problems, it would show up in a test like that. So that's the end of the slides I was going to go through, and I'm going to turn it back over to Jim to go over some of these processes we have in place to keep inclusions small and deal with things like that.
Very good. Thanks, Dan. Good job, Dan. Okay. Guys, any questions so far?
Do you guys make your own molds?
We don't at EQS, but we have a sister company called Elwood Engineered Castings that do. They're gray iron. They're made out of gray iron, gray cast iron. Something we don't produce, but they're a foundry. So most, if not all, of our molds right now are made by them. So our mold sizes, touch base on it real quick. With a wide variety of molds. 10-inch diameter would be our smallest mold, and we make all the way up to 69 or 60 by 79 cross section. And then most recently, we've just added an 82-inch diameter mold, which is actually a 2-heat pour. But pretty wide variety of, I don't know if I said it, 50, 56 different mold sizes. So, we're going to talk a little bit about, kind of circle back what Dan just kind of gave us a really good overview of what's happening through it. Kind of go back and highlight a couple of things. One of the most important things as a steel supplier we need to do, obviously, is we need to meet the chemistry. Hit the chemistry consistently and repeatedly, but we also need to deliver a clean steel consistently. One of the things that Dan talked about and how we do that, we've identified it. We were talking, break it down into 3 sections. Step one, clean steel practice and secondary steel making. That's starting effectively tapping out of the arc furnace into the ladle refining, and deoxidation of the steel through melting. Step 2, clean steel practice during bottom pouring, making sure when we pour the steel, like Dan had said, we're worried about exogenous inclusions. We have $100 million worth of steel making that can make the cleanest and best steel in the world. That would be step 1. Step 2, we can undo that in a heartbeat with a bottom pour practice. So all that hard work, all that time and effort, it goes by the wayside if we don't take care when we pour the ingots. And then finally, step 3, clean steel during solidification, making sure when we have our molds that we proper mold design, that we have proper practices, solidification times, not disturbing the mold, making sure we don't, again, undo what we've already done. And our goal is to ensure high quality steel is delivered to the forge shop consistently. So step 1, clean steel during secondary refining. If you remember back, in the arc furnace, we're blowing oxygen, right? We're blowing oxygen, we're getting rid of the carbon, we're getting this chemical heating, we're saving time, we're saving money, 20 minutes off of our tap-to-tap time. We got to tap that heat, we have 1,000 parts per million oxygen, okay? So number 1, we got to make sure that carbon's out of there, because if we tap with that much carbon and oxygen, we're going to get an explosion. So we get the carbon down. We have all this oxygen, which if we don't take care of this oxygen, we're going to end up with a very dirty steel. Oxygen is going to be free to react with any element that wants to tie up with oxygen, be it silicon, whatever. We want to make sure we take care of it and we control it. And how we can control it is using aluminum. By and large, 95+% of the grades of steel that we make at EQS are aluminum killed. Aluminum, of the commercially practical elements to use in steel making, has the highest affinity for oxygen than any other element. So if there's a molecule of oxygen there, and there's an aluminum, there's a silicon, there's a calcium. If they're all lined up, I shouldn't use calcium. The aluminum is going to go after that. Yeah, sorry, it's been a while. The Illingham diagram. So aluminum and silicon are standing there. The aluminum is going to react and tie up with that oxygen faster than the silicon can. Okay? So by adding the aluminum, we make sure that we're going to create alumina oxide. Why do we want to create alumina oxide? Because it's light. Okay? It's a liquid. When we form, when the heat is tapped into that ladle, onto the aluminum, on the bottom of all of that oxygen is reacting with the aluminum, assuming we have enough aluminum, which we do. And now we still have a ladle of 1,000 ppm oxygen, but now that oxygen is in the form of alumina oxide, Al2O3. It's a liquid inclusion, which theoretically, if we sat there and we let that ladle sit with our top slag, Stokes' law, those are going to float. Okay, they're all going to float up, and eventually, when they're going to come up to the slag, that slag chemistry is going to take over, and it's going to vacuum all those alumina inclusions up. But we're not that patient. That's where the induction stirring comes in, and by stirring the steel, we're getting more circulation, and we're having more of the steel come in contact with the slag than would be without. And as we do that, the alumina inclusions come in contact, more contact with the slag, and are absorbed. The longer we stir, and that's what this is showing us here. So here we are with our EAF deoxidation, 900,000 ppms. Within, time's not right, within about the first 10 minutes, we're dropping here, we're dropping down to about less than 100 ppm. And then by the time we're ready to tap, go to team, which is about an hour to 2 hours, sometimes longer, we've dropped the aluminum down to less than 10 parts per million. So the good news is we started off with high oxygen. We added aluminum to make Al2O3 alumina. Now we're stirring the alumina out, which as we stir the alumina out, the overall oxygen content comes out. So now we have a ladle full of clean steel. Now what we have to do is get it into the molds without having too much, without having any problems. So teaming temperature is critical. We'll talk a little bit about teaming flux and teaming speed. Okay? Now at this point, those oxygen, that Al2O3, as Dan mentioned, if there's going to be some residual alumina in there, that would be a small micro inclusion, an indigenous type inclusion, something that's coming from the actual liquid steel. What we want to avoid is creating any kind of exogenous inclusion. So the first thing we want to do is when we pour the steel, okay, you saw the trumpet, what's all around it? There's air all around it. So we've reduced this oxygen content, but what we want to prevent is that steel being exposed to the air. Because when the steel gets exposed to the air, it's going to want to what? React with that the oxygen in the air and reoxidize. And once again, we can't control what comes in contact with the oxygen in the air. So we want to prevent the steel from being exposed to the air. You saw that we're argon shrouding the stream from the ladle into the trumpet. And then when the steel comes down into the mold, what we're doing is we put this special flux. It's a fly ash-based black powder called teaming flux. Okay? And this teaming flux is sitting on the bottom of the mold, and when this hot liquid steel, and that's what this clear area is here, hits it, the heat from the steel causes this black powder to start to sinter. And then as it sinters, it actually ends up becoming almost a glassy lubricant. And it spreads out over the entire cross-section of that rising liquid steel in the mold. So if you can imagine, we're looking down in the mold here, okay? This, can you see this surface right here? That's the steel right there. But it's black and white, but trust me, it's not orange, it's black, because that powder is completely covering the mold as it's rising up. Okay? So we're not exposing the steel. The other thing that this flux is doing is that this glassy lubricant is also feeding down alongside the mold wall here, acting as a lubricant, so that the steel doesn't stick to the mold wall. And we end up getting a very good ingot surface quality as a result. That's the good part. The scary part is we do not want to mix this teaming flux with this liquid steel. So we have to control our teaming speed. On the ladle, there's load cells. And that load cell records the weight. And we're able to convert that weight over time into a pouring rate. So as we're pouring, we can say we're pouring 1 ton per minute, 2 tons per minute, 1.5 tons per minute. So we will actually cap how fast we pour the steel to make sure we don't pour too fast. Because if we start to pour too fast, and a standard rule of thumb is 6 inches per minute rate of rise. So 6 inches, I won't waste a minute here, but that's not very fast. But you start pouring that fast, it's going to start becoming turbulent. And then when it starts becoming turbulent, now this is getting disturbed. And now this flux is starting to mix with the liquid steel. And now we're playing with fire. Because maybe this can float back out, maybe it can't. If we're pouring too fast, we can risk entrapping teaming flux.
How do you control the speed?
We have a slide gate. Slide gate we have a slide gate here. It has a hole in it. Okay? And there's 2 plates. Do it this way. So that's in the open position. So we're pouring through here. What we can do is we can adjust this opening, and it constricts the flow. So now, if we do this, instead of having this as our width, now we're blocking this off a little bit. So now, this is our width, pouring width. So this would be wide open, and then we can adjust these slide gates, and basically by aligning the holes, we can control it. Now, what we do also is we now automatically feed that data, and we're sampling that pouring speed every 30 seconds. So we end up at the end of the heat, we end up with a very nice profile of what. Obviously, our operators, our guy that's pouring, our steel pourer, is monitoring the process himself visually, standing right there, making the adjustments as needed. But we also end up with a very good profile showing up. Now, when we pour, initially we pour wide open. First 2 minutes, 3 minutes, it's poured wide open. We have to fill the system, otherwise the steel will just freeze off immediately. So we pour wide open, 3 minutes, then we cut back, and then within 3 minutes, we need to be into our steady state teaming, maximum teaming, whether it's 1.0, 1.1, 1.3, and we're recording that as such. If we violate it, it ends up being a non-conformance, or worse, ends up being a cracked ingot or becoming a problem. Okay, clean steel during solidification. So now we've deoxidized the steel. We've successfully poured this ingot at a controlled rate of rise. We have not entrapped any teaming flux, which is good. What we have here, this is a finite model of an EQS ingot, a 49-inch diameter ingot. This is 15 minutes after pouring. We're going to kind of watch this solidify. If you look outside here, you have this gray shell right here. Then inside, you have this red line. That's the solidification front right there. That's the liquid solidifying. So the first thing that happens is the steel comes in, it hits the mold wall, and it chills. Okay? It chills. So what does that create? What kind of? It's going to create a chill skin. And then from there, we're going to begin to solidify. Now, I think Kyle talked about this. What kind of grains would then be produced in that area? There's chill. There's.
Come on, Chip.
Kelowna? Come on.
That's it. Columnar grains. And then as we get in the middle there, you end up with some equax grains as well. But right now, we are solidifying. Now something's happening here. Somebody tell me what's happening up here. Anybody? Anybody? This is solidifying slower up here than it is down here. The reason it is because we use what's called a hot top. If you can look here, you see these boards that are kind of wrapped around here. I don't know if you guys can appreciate that or not. It's kind of, somebody that knows, has looked at it. These boards, as this steel fills up into the mold, as soon as it hits these boards, these are made out of an alumina-based refractory, that as soon as they hit, the boards are going to begin to burn. Now some can insulate, but some will burn, okay? And when they burn, it gives off heat. And that heat slows the solidification process down. It's called an exothermic hot top or an insulating hot top. The reason we need the hot top is because the steel, we talked about it earlier, it shrinks when it solidifies. So if we did not have a hot top, the ingot that we deliver to Scott Forge probably will have a primary pipe cavity, I don't know, about as big as your head at the top, and it might go in, you might lose 50% of the ingot, you might lose 60, you might lose 40. It would be pretty variable, and it would be pretty unruly to try to make product consistently out of. So what we do is we put this hot top up here. It slows solidification and helps control the discard. We kind of control what we're going to scrap. So instead of losing 50% by using a hot top, we're able to lose 10, 15, worst case 20% on a very large ingot. But it's very defined, so when you guys forge, you see where the hot top junction is. If you crop at the junction, everything is going to be below that is going to be good. Because of the mold design, because of the hot top design, everything being figured and balanced to allow ideal solidification. here's our ingot now. We're 75 minutes in. You can see we're solidifying here. You look what's happening up in the hot top. See how it's delayed? You know, here we're about what? Let me just say that is about a third of the way solidified. Not quite half. Here we're not even 25% solidified. Talk a little bit about mold design that we use. This is a tapered ingot. Okay, a tapered ingot. See how this solidification front's progressing? If there's any inclusions left while this is solidifying, these things are still floating. We still get extra float time here. So it still allows some chances for inclusions to float. It also, and we're going to talk about this a bit more in a second. Tapered ingot allows the highest possible quality. A cylindrical ingot is straight-sided. Okay? The good news is on a cylindrical ingot, we're able to use a smaller hot top volume, okay, because of the straight side, and we're able to get better yield. So we're able to produce any air melt quality steel, bearing quality steel, whatever, to meet any air melt requirements and still get a 90% yield. Big end up, you have a bigger hot top volume, but you are able to get improved cleanliness. With the big end up ingot, I'll come back to that in a second. Here we are back. We're again back talking a little bit more. Here we see the ingot about 135 minutes, and you can see this hot top here being delayed. Solidification is progressing. And then finally, here's our tapered ingot. Last metal to solidify, very important, because the last metal to solidify, all the impurities, the most highly segregated part of the ingot, and any inclusions, most of the inclusions are going to get pushed with that solidification front. So if we can have the last metal to solidify up here in the hot top, here's our hot top junction, we know that everything else, or most everything else below that junction, is going to be very good. And the result is an ingot that once forged, able to produce approaching remelted cleanliness. You're going to have AMS 2304 if you're familiar with the premium quality spec. Also 16th inch flat bottom hole flaw sizes. So very, very high quality. And before we leave this, the thing I want to touch on here also that I don't have is the cylindrical ingot. Why the difference? A cylindrical ingot is straight-sided, and the solidification front is progressing this way, so that you do end up with the last metal to solidify along the center line of the ingot. So as a result, this hot top doesn't need to service this full ingot. It's really just worried about the top part of this ingot, so you don't end up with a primary pipe, and then you do end up with a little bit, but it's broken up and strung out over the center line of the ingot, so you're not getting one specific area of concentration in the ingot body. Certainly the cylindrical ingots are the highest volume of ingots that we produce at EQS, with a 31-inch ingot. I think it's still the highest use grade ingot of those that we make at Scott Forge. And then finally, clean steel during solidification. We talked about this whole time, making sure we don't disturb it. You know, if we were to strip it early, cut it early, this is still a mushy zone. So if we bump that, all that work and flotation, this last metal to solidify, it's a little time bomb sitting in there. So we don't want to bump it and allow it to move and possibly end up getting disturbed and ending up freezing below the hot top junction. And that's it on the clean steel portion. You guys have any questions? Make sense? How are we doing on time?
Doing pretty good.
Okay. Talk a little bit about hydrogen. Dan touched on about vacuum degassing. Hydrogen is dangerous. hydrogen is very dangerous because as a steel maker, we have to reduce the hydrogen because as a bulk unit. But once it solidifies in the ingot and it gets produced into a forging, the hydrogen that's in that matrix will move. It diffuses. And it diffuses over time. So what can happen is if you make a cross section, and this is a forged, I don't know, what size, Chris? What do we make this?
Well, let's say 30 inches.
30 inches, all right. So this is a 30-inch round-cornered square, which was forged. Number one, we have to make sure as a steel maker that the overall bulk hydrogen content of this steel is as low as possible, especially the larger ingot size, typically the larger cross-section that's going to be made. So there's going to be, if you can imagine, little hydrogen atoms in here. And what these guys are going to do is they're going to start diffusing, and they're going to start moving, and they're going to try to escape. So the hydrogen here, makes a run for the border. Bang, he's out of there. He's free. This stuff has got a longer way to travel. Okay? Now, the good news and bad news is we just talked about clean steel. So we have very few inclusions here. But what will happen is if we have a manganese sulfide, there's an inclusion there, an impurity. It can be anything. These hydrogen atoms are going to start accumulating at this area. Okay? The more hydrogen that accumulates at this area is going to create stress. The higher the stress, and it's a function of the steel grade and the strength of the matrix as well, the higher the stress is, you can actually get to the point where the stress created by this hydrogen exceeds the strength of the matrix. And what you end up with is a crack. And, in many cases, several cracks. And that's a defect called hydrogen flake. That's what we want to avoid. Ways to avoid it. One way is we put sulfur in the steel. So instead of having, which will create manganese sulfides, relatively harmless inclusion. Matter of fact, some people like to have sulfur added for these manganese sulfides because it helps the machinability of steel. Many of the grades we make for Scott Forge, we have minimum sulfur contents for machinability. So now, if I add my sulfides, and just to oversimplify, so if there was one, if I have 10 atoms, instead of having 10 atoms accumulate at one sulfide, that way I don't have to get fractional. If I have 5 manganese sulfides, well, maybe I end up with 2 at each. So I would rather have 2 at 5 of these than 10 at one of these. The stress is going to be much less. Okay? So anyway, that is what hydrogen, that is what can cause hydrogen flake. So what are we going to do to prevent it? Well, first we're going to put the right cap on the right marker, right? Sorry. Again, just to go back and review and reiterate, we want to refine the hydrogen from steel using vacuum degassing. The more we expose the steel to the vacuum, the better job we're going to do reducing it. One of the advantages EQS has, most steel makers use argon only. We have argon and induction. Induction stirring is unique, not exclusive, but pretty unique to EQS. So if you look, just as a difference here, you see this dotted line and you see this solid line. This is kind of giving you an idea and difference in stirring energy. So say this dotted line, this solid line, is in argon only. This dotted line is showing you what might happen with the combined stirring energy of induction stirring and argon bubbling. Being able to refine more hydrogen, use that vacuum. Dan had a good analogy with the little fine particles. The more steel we can expose to the vacuum, the better job we're going to do refining it. And that's where the stirring energy, having a more stirring, stronger vacuum to remove those particles. We want to prevent hydrogen pickup. When we team, we're teaming in air, and there's moisture in air. We need to preheat the molds. We have a lot of heat. So what an enemy is condensation. So rather than pouring cold molds, we will actually preheat the molds before we bring them into service. And then once they're in service, they're in a hot environment, so there's natural high level of heat to prevent condensation. But a little bit of condensation on a mold is a hydrogen pickup. We also, argon shroud, also helps us guard against maybe about 1/10 of a ppm pickup during teaming as well. So those are two important parts. One of the other things is measurement. We measure the hydrogen after vacuum degassing in process. So if we're working to a 2.0 part per million specification from Scott Forge, after vacuum degassing, we work to 1.5 maximum because we know that we will pick up hydrogen in the atmosphere, statistically about 1/2 part per million. So what we're doing is, at the end of a good degassing cycle, we'll take our hydrogen sample. If it's 1.6 or 1.7, we go back and re-degas until it's 1.5. And then, as we saw in the video, on teaming, just before that steel fills into that hot top, at the very last moment, to get the very last possible snapshot of the hydrogen that's in that steel, we'll take a hydrogen sample as well. And actually, we end up getting 3 values. And of those 3 values that we get, we certify the highest. We always err on the side of caution with hydrogen. All other elements, carbon, manganese, we'll average those together because, well, that's just the way it's done with ASTM. But with hydrogen, if we're working to our 2.0, and we have a 1.8, a 1.9, and a 2.1, that heat's certified as a 2.1, even if it means that heat is non-conforming and has to be dispositioned in another manner rather than going to the customer. Always erring on the side of caution with hydrogen. The other thing we can do is resist hydrogen, and this is kind of steps out of EQS and more in the Ford shop. Have you talked about phases, Kyle? Austenite and whatnot?
Mm-hmm.
You guys have you talked about retained austenite at all?
No.
Okay. One of the things we want to try to do is resist the stress. You know, we saw that with just the crude drawing I just made where you saw the hydrogen atoms accumulating. If you have a brittle matrix because of the microstructure, if it's going to be brittle, it's going to be less resilient to the stress that's created. Okay? So what we can do is, once forging on flake-sensitive grades, flakes, and section sizes that are deemed to be of concern, from forging, we will cool as fast, air cool, and fully transform the steel to usually about 500 degrees Fahrenheit. Then come back and give it a 1200 degree temper, basically tempering the matrix to make it more resilient, and then air cool, and then send it on for either further heat treatment or further machining, whatever may be happening next. The reason this cool down is so important is because some grades, especially nickel bearing grades, microstructurally, if you were to slow cool those, you could end up with a phase called retained austenite. When we're up here at forge temperature above 1600 degrees, the microstructure is predominantly austenite. When we cool down, we end up with ferrite, pearlite. Maybe if we cool fast enough, we create a phase called martensite or bainite, harder phases. But with some grades, they're sluggish to transform. So if we slow cool, you can end up with these islands of retained austenite. And here's the problem. Retained austenite has 6 times higher solubility. Hydrogen has 6 times higher solubility in retained austenite than it does in ferrite. So 6 times. So what's going to happen to that hydrogen? It's going to want to go into that retained austenite. So that retained austenite then ends up being the same scenario that we have with that manganese sulfide, where the hydrogen's accumulating there. We have these little islands, these little time bombs sitting in there of retained austenite that have very high localized concentrations of hydrogen. And eventually, over time, this retained austenite transforms to martensite. Very hard, very brittle, and at that point, it can crack and also create hydrogen flake. So the matrix, by cooling, preventing retained austenite, and then tempering the matrix, making it resilient. Very important to resist hydrogen stress in forging. Make sense? Any questions? No? Okay. We're going past 5, I'm sorry. We'll rip through here. You know, we're talking about ingot, you know, in our world, Scott Forge and EQS, we have very specialized application making bottom poured ingots. The majority of steel today is produced via continuous casting. Okay? Continuous casting, well, not similar. You can see what happens with continuous casting. Here's our ladle of steel. The steel is exiting, but instead of going into the trumpet and then into the mold, it goes into this vessel, this little container right here. That container is called a tundish. And that's kind of a holding tank, if you will, for the steel. And then at the bottom of the tundish are molds. They're copper-cooled molds, and we'll see a cross-section here in a second. And that chills the steel into a shell. And then as it comes, it's pouring through here into these molds. And then as it comes through the molds, there's water spraying, and these rollers extract the solidifying steel so that as it's coming out, you know, the shell is solidified, and then by the time it gets to here, it's just about solidified. And then then it becomes an as-cast slab. It could be a bar, it could be a round, it could be a square. And as it comes down here, there's a series of torches, and it just cuts the section off one at a time. The thing that makes this so advantageous is it's continuous. So for very high volume, same grade, same size, heat after heat after heat, this is the way to go. Because you fill this tundish up, and look at this turret up here. Once this ladle's empty, this turret spins 180 degrees, and bam, this ladle is here, and it's pouring. And then the ladle that is empty is removed, and a new ladle comes in and is staged, waiting for this ladle to finish. So it's a continuous operation, because this tundish kind of is the buffer zone. It's a little bit of buffer. So it always has steel, liquid steel here, filling these molds. Here's a cross-section here of what's going on here. We have the ladle, and then it's, again, shrouded. Don't want to expose the steel to air. Into the tundish. In this case, this is showing a stopper rod, a way to adjust the pouring rate. Again, we're controlling the pouring rate out of the tundish and into this copper-cooled, water-cooled mold. It's copper, so you can see here it's bright orange, and as you get further down, you can see this darker orange. I don't know if you guys can see that very clearly or not. You can see this shell getting thicker and thicker and thicker until we get down in here, and it's pretty much solidified, and it chops it off. So then also here you've got a slag layer covering the bath, so we're not exposing the bath to the air. Also have usually we'll have a ladle cover here to help keep the heat, minimize the temperature loss during teaming. Spray chamber, again, it's all being done at a controlled fluid. And without going too much, that's continuous casting. Now, there are applications that Scott Forge make and other people make that air melt either for liability reasons or for property or cleanliness reasons just aren't sufficient, where you have an aircraft component, a landing gear, a critical gear in a power shovel, which you just cannot stand any maintenance outage, like the was that P&H? P&H, 4340 VAR. Trying to think of some other VAR applications, B50, A977, but they're very critical applications. You know, the tapered ingot's very good. It's capable of a 16th-inch flat bottom hole, but it's a giant hole solidifying. So segregation will be greater than what you would get in a remelted ingot, and we'll talk about that in a second. So when you need extremely demanding applications, you can go to remelting, and there's two different ways to remelt. Vacuum arc remelting, where you take an ingot effectively and you remelt it drop by drop in a vacuum, or electroslag remelting, where you take the ingot again, it becomes the electrode, the carbon electrode, and you melt it drop by drop. Except the steel, in this case, is going through another slag, and as it goes through the slag, it gets even cleaner and then resolidifies below. This is just a schematic here of VAR, this giant chamber. Down below here is a crucible. This black stick is our ingot. That's the ingot that we just produced at EQS. We've cropped it, and now we have an electrode holder that's welded to it. We lower it into this chamber, hang it here, cover the chamber, and then we begin to pump. This becomes a vacuum chamber. And then we pump the vacuum down, and we strike an arc, and then we remelt the ingot from here, and then the drops begin to form down here. And now we're remelting a larger ingot. So if this was a 20-inch diameter ingot, we might remelt it into a 24-inch crucible. So the 20-inch air melt ingot gets remelted to a 24-inch, as an example, VAR ingot. And again, drop by drop. This electrode is melted until it's completely consumed, and it is reformed as this VAR ingot. And our man Dan has done another great VAR simulation. So let's see how this, see how it works. Now here we have, this is a water-cooled jacket here. Here's our electrode. Here's our hanger here, and now we're going to shoot it with electricity. You can see the other ingot reforming. As this is consumed, you can see the new VAR ingot forming below.
Each drop is exposed to the vacuum.
Yes, each drop is exposed to the vacuum. Would help with hydrogen. Hydrogen is further refined, and also any non-metallic inclusions. While they may not, some of them may be pushed to the surface of the ingot, which is then subsequently ground, but some may remain, and those that do remain can get broken up into a smaller, less detrimental configuration. Now you're looking at defect sizes. If we think of 1/8 of an inch for cylindrical ingots, a 1/16 of an inch ingot, a 1/16 of an inch for tapered ingots. Now for VAR and ESR, 3/64, kind of the acceptable maximum flaw size, generally accepted. Do you want to see that again, or are we good with that? Okay. ESR melting. Similar setup, except it's not in a vacuum. And the difference being, when we here, instead of this being in a vacuum, in this layer right here, we have flux, which basically is a lime flux. And there's chemical reaction going on. As the steel goes through that, any inclusions chemically react with that flux and are absorbed into the flux, and the liquid steel passes through the flux into the solidifying ingot below. Same type of principle. Electrode hung here, electrode holder here, crucible here. Current drives from the source through the electrode, melting the electrode at the tip, and then through the flux, and then they're solidifying, resolidifying ESR ingot below. So the difference between VAR and ESR, VAR is under a vacuum, ESR uses a slag for improving the quality. The other thing is, because it melts drop by drop, the segregation of the material. Have you talked about segregation at all?
Mm-hmm.
The segregation of the material is much better. It's the difference between very small pools solidifying versus very large pools. You have very any questions? Just to kind of wrap up, benefits of using state-of-the-art steelmaking. Final product costs are low. We're an efficient, the EQS, go turn into the sales guy here. EQS has a very good balance. We have world-class productivity in our arc furnace in our melt shop. So we're able to melt, as quickly and as efficiently as anyone in the world. But we also have the quality drive, not that others don't, but we make, instead of making 1 or 2 grades very quickly, repetitively, we make 300, 400, 500 different grades of steel, all with varying applications, all with varying quality levels. And we're able to, with ladle refining and bottom pouring and the technology that we have, able to produce world-class quality in addition to world-class productivity. And by doing that, any kind of rejections or anything that you would need to deal with, either we would need to deal with internally because of inconsistent production, causing delays delivering material to Scott or low. Delays processing here at Scott because of problems are reduced. And responsiveness. The things we can do with our steelmaking equipment and chemistry control, we can make very tight chemistries, process-wise, it's extremely repeatable. We talk about teaming temperature as an example. It's a 0.5% variation in our teaming temperature window. So if we supply 75 heats of 4340 to Scott Forge in one ingot size or various ingot sizes, the variation in the teaming temperature will be less than 0.5%. The chemistry will be extremely tight and consistent, so that when you're looking at heat chemistries from one to the other, they're practically identical. There's some variation, obviously, but they're practically identical. So that when you get to the heat treat and the various operations that you guys will do as far as getting mechanical properties, as far as your customer heat treating and getting mechanical properties, it'll be very repeatable, very consistent. It's not good. If you look at a specification for 4340, the industry specifications are very wide. You can send a heat of 4340 at the top end, a heat of 4340 at the bottom end, and they're going to act almost like 2 separate grades. So if you're getting the same type chemistry, heat after heat, it's going to be very reliable and predictable. Our goal is to optimize.
Your question. What
Yes.
determines the heat number?
What determines the heat number? It's a sequential number. It's just a running number. So when we started in December of 1985, somewhere somebody said we're going to have the alpha numeric and then a 4-digit number after. So it's A0001. And then from there we just kept rolling through 2, 3, 4. Once we used those up, we went to B, C, D.
So it has nothing to do with the makeup of the metal or anything like that?
No, it's a sequential number that's not random, but it's a sequential number that every heat that we make goes from. Now, one thing we would just to touch on as far as grades, with that liquid heel, when we make steel in a production night, we'll schedule 27, 28 heats in a given night, and what we want to do there is we want to build the alloy content of that heel. So we'll start off with carbon steel, and then go to 4140, then 8620, 4340, and then HY80s, 3% nickel steels, rotor steels, things like that. Then if we have stainless to make, we might come back with a lower nickel, 8600, or like an F22 where there's a higher nickel tolerance, and then we'll go back and make our stainless steels, which we make effectively. It's a carbon steel charge when we make a heat of 410. So that's it. Thank you very much. If you guys have any questions, happy to answer them, Dan or I.
Yeah.
We appreciate you guys taking a few minutes today and listening to our talk. Hopefully it was somewhat useful for you. And no questions? Then we get to the giveaway part of our. We brought along some pens because we know Kyle's going to give you a really